keynote speaker, Professor Ho-Kyung Kim. He's POSCO Chair Professor at Seoul National University with extensive expertise in bridge aerodynamics, structural health monitoring, and infrastructure resilience. Professor Kim has played a key role in numerous cable-supported bridge projects and holds prominent positions in international organizations such as IAPSI, EAWE, and IAPMAS. He also directs the Floating Infrastructure Research Center at Seoul National University. His keynote is titled Korean Bridge Design, 30 Years of Innovation for a Dynamic Society. Please welcome to Professor Kim.
Thank you, Mr. Chairman. Good afternoon, everyone. It is a great honor for me to deliver a keynote presentation today. For those who still do not know Korea, here are some facts about South Korea. It is located at the eastern end of the Asian mainland, with China, Japan, and Russia as its closest neighbors. South Korea occupies the southern half of the Korean peninsula without a direct land connection to the Eurasian continent. In addition, the country is home to more than 3,000 islands scattered along its coastal lines. Also popular for K-pop and K-food, thanks to YouTube and Netflix. This is the traditional Walljeong Bridge, originally built in AD 760 during the unified Silla period. After the Korean War, the country began reconstruction in the 1950s as a UN aid recipient and has become a major UN contributor today. This was made possible by the Miracle on the Han River led by conglomerates like LG, Hyundai, Lotte, POSCO, and Samsung. Today, Korea is the world's 13th largest economy by nominal GDP. The economic boom was supported by continuous infrastructure development. The Seoul-Busan Expressway in 1970, Incheon International Airport in 21, Korea's high-speed railway 24, and National Road 77 stretching 1,200 kilometers along the west coast in 2028. Our research began in the mid-1980s with the development of analysis programs covering elastic catenary cable elements, initial configuration and equilibrium analysis, and construction stage analysis. These analysis programs were later applied to the Yeongjong Bridge, a self-anchored suspension bridge with a three-dimensional main cable. Unlike earth-anchored types, the self-anchored system required a very different construction process, demanding more precise cable analysis. We have merely 3 long-span bridges before 1985. The entrance in the 21st century was a turning point in the Korean bridge technology. Seoul Bridge and Yeongjong Bridge were completed in 2000, and Hwanghan Bridge opened to traffic in 23. In 26, we developed the design guidelines for steel cable-supported bridges, relying on allowed stress design under the auspice of the Korean Society of Civil Engineers. In the same year, these design guidelines were adopted for the design of the Isunsin Bridge. This picture was taken at the first symposium on sea crossing bridges at the time, showing some former and current Korean Vice President of IFC. The Isunsin Bridge was completed in 2013, and there was a sharp increase in the number of long-span bridges. The Isunsin Bridge is the longest, with a main span of over 1.5 kilometers. The gap between the twin decks was reduced to 4.3 meters through intensive wind tunnel testing. At the dawn of the new millennium, Incheon International Airport opened with Terminal 1 in 2021 and expanded to Terminal 2 in 2018. Sea crossing bridges were built as the airport grew, and the third connecting bridge is currently under construction and will be completed next year. The number of passengers has increased steadily, reaching 80 million today. This demonstrates the important role of infrastructure in promoting social development and enhancing international connectivity. During this period, we were planning the Value Create 10 R&D project under the Ministry of Construction and Transportation, with the Super Longspan Bridge project as one of its flagship initiatives. As an outcome of the Super Longspan Bridge project, we developed a reliability-based design code targeting a 200-year design life. The target reliability was set at 3.7 to 4 point for traffic live loads to unify load combinations and load factors across long and medium span bridges. We introduced 3 non-dimensional load ratios. We adopt lower beta values for lateral loads such as wind and earthquake to account for higher variability when dead load contribution is minimum. For code calibration, we introduced the concept of RRD, the ratio of return period to design life. RRD was set to 12 for wind, giving a target reliability index of 2.0, and 24 for earthquake, resulting in a target index of 1.5. Jeollanam-do is the southernmost province in mainland Korea and comprises 1,891 islands, of which 400 are inhabited. Jeollanam-do has developed a diamond-shaped networking linking its major islands, with the longest connection being the 8-kilometer Cheonsa Bridge. To mark the opening of the Cheonsa Bridge, Jeollanam-do held its second symposium in 2019. The picture was taken during the technical tour, and you can see Korean Vice President and some familiar friends who are here today, President Tina. The world's longest Çanakkale Bridge opened to traffic in 2022. Two Korean companies, DL ENC and SK, built the bridge with two Turkish partners and are now operating it. As of today, we have built 85 long-span bridges, including 11 suspension and 74 cable-stayed bridges. Most are located along the coastal National Road 77. Overseas market share in long-span bridge construction increased immediately after the R&D project, supported by a strong track record as shown here. High-strength wires for suspension bridge main cables were developed by POSCO and KISS Wire. In the 1990s, 1.5 to 1.7 gigapascal was used. From the Isun신 Bridge, we applied 1.86 gigapascal, then 1.96 gigapascal for the Ulsan Bridge. These wires were also supplied to the Çanakkale Bridge. And we are now applying 2.16 gigapascal for an ongoing project. Very recently, a concrete cable-stayed bridges with a 540-meter main span was opened over the Han River in Seoul. Using 80 megapascal high-performance concrete, it was honored as a finalist for this year's IFC Award in the large road and rail bridges category. UHPC was also developed by the Korea Institute of Construction Technology under the Super Bridge 200 project, targeting a compressive strength of 180 megapascal. And it was later applied to the Chuncheon Bridge. Let me now share some case studies on long-span bridges I have worked on, focusing on aerodynamic issues in wind engineering. This is the Jindo Bridge. The first bridge, one of the first generation bridges, was built in 1984. 20 years later, a second bridge was constructed as a twin bridge to accommodate increased traffic volume. The gap between the two decks is around 10 meters, and both use guide vanes to mitigate vortex-induced vibration, and it works well for the first bridge. This video shows vortex-induced vibration in the new bridge. Interestingly, the wind is blowing from the left side, causing the upstream deck to vibrate. Since many engineers found the upstream deck vibration unusual, wind tunnel tests were conducted. With wind blowing from the back of the model in this video, it was confirmed that the upstream deck could indeed vibrate. Removing the downstream deck eliminated this vibration. To clarify the interaction between the two decks, a PIV test was performed. The right image shows wind flow for the single deck case, with dark blue indicating near zero wind speed. The left image shows flow between two decks, where sky blue streams highlight amplified vortex trails behind the upstream deck, inducing its vortex-induced vibration. Changing the distance between the decks weakens this vibration, showing that the 10-meter spacing happened to be the most unfavorable choice. We also performed operational model analysis to determine the damping ratios of both bridges using data from built-in sensors. On the left, each circle represents the estimated damping ratios for the 20 minutes data. The average damping ratio of the new bridge was 0.29%, much lower than the design value of 0.4%. In contrast, the right shows the old bridge with a damping ratio of 0.63%, higher than that of the new bridge. In conclusion, the cause of vortex-induced vibration can be summarized as first, unfavorable deck spacing, and second, unexpectedly low structural damping of the new bridge. This is a particular concern for recent bridges that use high-strength steel and simplify welded details. Next is Cheonsa Bridge. Personally, it is my favorite as its bundled stay cables create a harmonious aesthetic. The bridge has high and low pylons with concrete decks on the approaching span and a steel deck in the central main span. A moving scaffolding system was used for the approach spans, as shown in Figure 1, and the pre-cantilever method was applied at the pier table of pylons, as shown in the second figure. The third figure shows the completed concrete deck spans. Afterwards, the steel deck of the main span was constructed with strong tie-downs provided by the bundled cables for aerodynamic stability during construction. Although the bridge was well designed, vortex-induced vibration was reported soon after its opening.
섬과 섬을 잇는 10km의 대교가 차로 다니면 출렁이는 그런 대교가 있다고 합니다.
지난 4월 개통한 신안군 천사대교. 전체 10.8km 구간 가운데 사장교 구간 모습입니다. 차량이 지나가는데 다리 상판이 위아래로 심하게 움직입니다. 지나던 차량들은 속도를 줄이고 운전자들은 불안감을 감추지 못합니다. 한국시설안전공단은 이날 천사대교의 상하 진동폭은 72cm로 교량을 편안하게 이용할 수 있는 사용성 기준 범위 25cm를 배 이상 초과했다고 밝혔습니다.
So it is a news broadcast at the time, and this vortex-induced vibration was caused by the incorrect positioning of maintenance rails beneath the deck. The bridge owner installed tuned mass dampers to suppress this first small vibration. The deck's vortex-induced vibration was effectively suppressed by the tuned mass dampers, but additional issues arose with stay cable vibration. On the left is high-frequency vortex-induced vibration observed in most long stays, which is common and can be controlled with dampers. On the right, however, is low-frequency vibration observed specifically in cable 34. That is not the longest cable as shown in the figure. So this is low-frequency vibration for specifically cable 34. We investigated the cause of this low-frequency vibration using CCTV images provided by the bridge owner, recorded during the vibration of cable 34. On the left, the cable begins to vibrate. The clip is shown at 8 times speed. At this stage, 3 vertical modes are observed, as shown here, 0.3, 0.4, 0.5 from the deck. That is induced by the tracking. And as the wind speed exceeds 10.5 meter per sec, the right shows the maximum vibration of cable 34. You can find out. At the moment, the deck vibration was only 6 Gauss, too small to be visible to the naked eye. The vibration frequency was 0.433 Hertz. The second mode is dominating at this moment, corresponding to the second vertical mode of the bridge deck. At the same time, the first natural frequency of cable 34 was also identified, 0.433 Hertz. This represents a rare case of resonant cable vibration caused by small support excitation. This study demonstrates that deck vortex-induced vibration must be suppressed even when amplitudes are well below serviceability limits of the bridge deck. Next is the double deck Gwanghwan Bridge. 2 rollover accidents occurred within 1 hour, both at nearly the same location on the low deck. As shown in the figure, the suspension bridge has truss members on the side, but the approaching span without truss members and exposed to side wind. The approaching spans also include a curved section. We performed wind tunnel tests and found an increase in wind speed over the lower deck. We conducted wind tunnel tests to measure aerodynamic forces on a vehicle using load cells in a trunk model. Since the vehicle moves along the bridge, the wind incident angle constantly changes, so we implemented a system to account for this variation. This allowed us to determine aerodynamic coefficients in terms of the incident angle, quantify the increased wind load on the low deck. This is known as the tunneling effect. Here is the framework for assessing vehicle instability. First, we perform wind tunnel tests, and second, vehicle simulations using traction. By varying the wind direction, we can identify the critical wind speed for accident for each wind direction. So in this figure, critical wind speed curve, we can find out the most vulnerable wind direction is south, and critical wind speed around 15 to 20 meters per second. If we combine long-term wind and rainfall data inside, we can evaluate risk index in terms of accident frequency. Under the regular driving speed of 80 km per hour, we identified 3 hotspots. We also examined 3 types of vehicles. The truck was the most vulnerable, especially on the low deck approach spans, where traffic accidents were observed. The critical wind speed was relatively low, around 15 meters per second, in terms of 10-minute average wind speed. By reducing the vehicle speed to 40 km per hour, the critical wind speed increased by 2 to 3 meters per second, reaching about 70 meters per second on the low deck for the truck. Based on this, we propose the following traffic control protocol. When wind speed approaches 50 meters per second, the speed limit is reduced to 40 km per hour. At 70 meters per second, the lower deck is close to high-sided vehicles. At 20 meters per second, all lanes are close to high-sided vehicles. The bridge owner accepted and simplified this protocol for implementation. I would like to conclude my presentation with a vision for long-span bridge technology. For the midterm to 2035, focus should be on high-performance materials, a shift in design paradigm, diversification of crossing method, and AI-based operations such as Bridge2X. For the long term, up to 2050, key issues will include intercontinental links, carbon neutrality, and automation. We need to consider new bridge types such as Hyperloop and submerged bridges. New materials and morphological optimization will continue to be developed to reduce carbon footprint, and multifunctionality will be increasingly required as bridge functions expand. This is a sketch of multifunctional bridges developed in discussion with engineers. So you can find your integrated mass transit, automated logistics conveyor system, utility gas, electric lines, and even Hyperloop. Until now, we have focused on expanding span length of the bridges, but I would like to propose more flexible bridge types that can accommodate large displacements and deformation while maintaining serviceability both above water and below the sea. A few years ago, we launched the Floating Infrastructure Research Center, FLORA, focusing on expandable modular floating platforms and floating bridges. These are our FLORA members, and we will begin constructing a test bed in this harbor next year. Thank you for your attention.
Thank you very much for your
very interesting presentation. There is some time left for one or two questions, if there are any from the audience.